Hi, everyone. I'm Kiara McKenney, and on behalf of the Applied Technology Council, I'd like to welcome you to this webinar on FEMA P-1026, Seismic Design of Rigid Wall Flexible Diaphragm Buildings, an Alternative Procedure. This webinar is brought to you by the Applied Technology Council under a contract with FEMA, the Federal Emergency Management Agency. If you haven't already, please go ahead and download the handouts using the link that's provided in the chat. We know that many of you are interested in receiving professional development hours for your attendance today. For those of you who registered and are in attendance at the webinar, a certificate documenting professional development hours will be sent by email to you within 4 weeks. If at any time during the webinar you have questions, please go ahead and type them into the Q&A window that you can open up from in the Zoom control panel. We're planning to have a live question and answer session at the end of the webinar today. Please go ahead and submit your questions as you have them rather than waiting at the end to submit them. And we will try to get through as many questions as we can in the time allotted. And if there are any that we are unable to get to, we do plan to provide written responses to them after the webinar. I would now like to turn it over to Patia Scott from FEMA's Earthquake and Wind Programs branch, who will provide a brief introduction to today's webinar. Patia, please go ahead.
Thanks, Kara. Good afternoon. As Kara said, my name is Patia Scott. I'm a civil engineer for the Federal Emergency Management Agency's Earthquake and Wind Programs branch. It's my pleasure to welcome you to today's webinar. This webinar was developed for the recently updated FEMA P-1026 Seismic Design of Rigid Wall Flexible Diaphragm Buildings, an Alternate Procedure. The updated report makes its second edition since its first publication in 2015. The new report includes additional research results, improvements to the original alternate procedure, and illustrative examples. It is another technical guidance resource for design practitioners. FEMA would like to thank ATC and the project team for the great effort they put in to update FEMA P-1026 and provide this webinar. And FEMA would like to thank Dominique Kelly, chair of the project team, and delivering this webinar today. Rigid wall frame, this is so hard to say. Rigid wall flexible diaphragm buildings are a common type of construction in the US. They are potentially vulnerable if not properly designed and constructed. Such buildings suffered severe damage or even collapse in past earthquakes. The new alternate design procedure improves seismic performance of rigid wall flexible diaphragm buildings. FEMA's National Earthquake Hazard Reduction Program, which we call NEHRP, is proud to sponsor this study and the development of the report. We are glad to note that the new procedure has been approved by the 2020 NEHRP recommended seismic provisions and adopted by the ASCE 722 standard, which is also adopted by the 2024 International Building Code. Hopefully, design practitioners will soon be able to use the new procedure. FEMA NEHRP is committed to work with the engineering community to continuously support improvement for seismic design of buildings and best design practices. Thanks, Kara.
Thanks, Fatia. So now let me introduce you to your incredibly accomplished presenter today. Dominic Kelly is a senior principal at Simpson, Gumpertz & Hager and practices out of its Waltham, Massachusetts office. He was project technical director for the development of FEMA P-1026. Dominic has more than 35 years of experience in structural engineering consulting. His practice includes design of new structures, evaluation of existing structures, repair and strengthening of structures, and structural investigations. He has been a member of ASCE SEI Seismic Code Subcommittee and NEHRP's Provision Update Committee at various times during his career, and he has been a member of the ACI 318 Building Code requirements for structural concrete for the past 20 years. I would now like to turn the webinar over to Dominic.
Thank you, Kiara. I'm excited to be here today to talk about this very important building type. It's really a vital piece of information.
Hi, everyone. I'm Kiara McKenney, and on behalf of the Applied Technology Council, I'd like to welcome you to this webinar on FEMA P-1026, Seismic Design of Rigid Wall Flexible Diaphragm Buildings, an Alternative Procedure. This webinar is brought to you by the Applied Technology Council under a contract with FEMA, the Federal Emergency Management Agency. If you haven't already, please go ahead and download the handouts using the link that's provided in the chat. We know that many of you are interested in receiving professional development hours for your attendance today. For those of you who registered and are in attendance at the webinar, a certificate documenting professional development hours will be sent by email to you within 4 weeks. If at any time during the webinar you have questions, please go ahead and type them into the Q&A window that you can open up from in the Zoom control panel. We're planning to have a live question and answer session at the end of the webinar today. Please go ahead and submit your questions as you have them rather than waiting at the end to submit them. And we will try to get through as many questions as we can in the time allotted. And if there are any that we are unable to get to, we do plan to provide written responses to them after the webinar. I would now like to turn it over to Patia Scott from FEMA's Earthquake and Wind Programs branch, who will provide a brief introduction to today's webinar. Patia, please go ahead.
Thanks, Kara. Good afternoon. As Kara said, my name is Patia Scott. I'm a civil engineer for the Federal Emergency Management Agency's Earthquake and Wind Programs branch. It's my pleasure to welcome you to today's webinar. This webinar was developed for the recently updated FEMA P-1026 Seismic Design of Rigid Wall Flexible Diaphragm Buildings, an alternate procedure. The updated report makes its second edition since its first publication in 2015. The new report includes additional research results, improvements to the original alternate procedure, and illustrative examples. It is another technical guidance resource for design practitioners. FEMA would like to thank ATC and the project team for the great effort they put in to update FEMA P-1026 and provide this webinar. And FEMA would like to thank Dominique Kelly, chair of the project team, and delivering this webinar today. Rigid wall frame, this is so hard to say. Rigid wall flexible diaphragm buildings are a common type of construction in the US. They are potentially vulnerable if not properly designed and constructed. Such buildings suffered severe damage or even collapse in past earthquakes. The new alternate design procedure improves seismic performance of rigid wall flexible diaphragm buildings. FEMA's National Earthquake Hazard Reduction Program, which we call NEHRP, is proud to sponsor the study and the development of the report. We are glad to note that the new procedure has been approved by the 2020 NEHRP recommended seismic provisions and adopted by the ASCE 722 standard, which is also adopted by the 2024 International Building Code. Hopefully, design practitioners will soon be able to use the new procedure. FEMA NEHRP is committed to work with the engineering community to continuously support improvement for seismic design of buildings and best design practices. Thanks, Kara.
Thanks, Fatia. So now let me introduce you to your incredibly accomplished presenter today. Dominic Kelly is a senior principal at Simpson, Gumpertz, and Hager and practices out of its Waltham, Massachusetts office. He was project technical director for the development of FEMA P-1026. Dominic has more than 35 years of experience in structural engineering consulting. His practice includes design of new structures, evaluation of existing structures, repair and strengthening of structures, and structural investigations. He has been a member of ASCE SEI Seismic Code Subcommittee and NEHRP's Provision Update Committee at various times during his career, and he has been a member of the ACI 318 building code requirements for structural concrete for the past 20 years. I would now like to turn the webinar over to Dominic.
Thank you, Kiara. I'm excited to be here today to talk about this very important building type. It's really a vital piece of infrastructure for our commerce, given that this building type houses large distribution centers, warehouses, retail space, and even suburban office parks. So it's a very popular building. If you ever look from overhead or bird's eye view, you'll see that many of these buildings are in the surrounding outlying areas of major metropolitan areas. Okay, so the learning objectives today are to understand why this document, FEMA P-1026, was originally created and why it's now being updated, become familiar with the content of the updated report, become familiar with the alternative procedure as it was incorporated into ASCE 722, Learn about the FEMA P-695 evaluations used to develop this alternative procedure and why we think it's better than the current procedure. And then learn about how this procedure is different from the traditional procedure. Some of the shortcomings of the traditional rigid wall flexible diaphragm building design is that it uses the equivalent lateral force procedure at ASCE 7, and which is really focused on the vertical elements of the seismic force resisting system. But for most of these buildings, these rigid wall flexible diaphragm buildings, the primary seismic response is really dominated by the deformation and yielding of the horizontal flexible diaphragm. And the ELF procedure, as it's written right now, does not account for this diaphragm deformation, the diaphragm response. And so and actually, when we did numerical studies of the probability of collapse using FEMA P-695 methodology, it suggested that the rigid wall flexible diaphragm buildings as they currently are designed may not meet the targeted expected performance for buildings designed in accordance with ASCE 716. So the presentation outline, I'm going to go over introductory materials, a summary of the procedure, status of the alternative procedure. Then I'll go into a description of these buildings and their performance in past earthquakes and talk a little bit about the potential issues in future earthquakes. The third part will be describe differences in seismic response of rigid wall flexible diaphragm buildings versus those of a typical multi-story building. Provide an overview to the ASCE 7 requirements for this alternative procedure, and then show a comparison of the designs using a traditional approach versus the alternative procedure. Present some of the results regarding studies justifying the alternative procedure, and then talk about recommendations for additional studies, and finally the conclusions. The second edition, the project team consisted of Mike Tong was the project officer and Bill Holmes, the technical monitor. Applied Technology ran the project. The project technical committee consisted of myself, John Lawson, Kelly Cobean, and Ben Schaefer. It's a very strong team, and with a working group consisting of Shahab and Maria, the lower right. And then we had a very strong project review panel, many of which the members were from the original first edition project team, in which the original version of that, John Lawson, he authored many of the chapters in the main body of the report, and I wrote the appendices and edited the front portions of the report. And had contributing authors who were also Andre Filatro and his student at the time, Maria Kolayu, at the time they were both from the University, SUNY Buffalo. Reviewers, once again, very similar, such as Kelly Cobean, who was then on the project technical committee this last time, and several other project review panel members, we had very good input from not only materials representatives, but also designers of this building type. The chapters in P-1026 are the introduction. These kind of match what we're going to talk about, the order in which I'm going to present things in this presentation, but slightly different. There's the introductory chapter, then a description of the rigid wall flexible diaphragm buildings and their performance in earthquakes in the past. Traditional design practice, we provide examples for both, in this version, we provide examples for both not only wood diaphragm buildings, but also bare steel deck diaphragm buildings. Chapter 4 is development of the alternative procedure, how we came about in developing it. Implementation is chapter 5. How do you actually implement this procedure? And then chapter 6 is the diaphragm deflection check and how important that is. So we spent some time with that. And then chapter 7 is more of a summary chapter in which we're comparing the design results from the traditional practice versus the alternative design procedure. Chapter 8 deals with future studies for this building. And then chapter 9 is the conclusions. So the origins of this procedure really are founded in the poor performance identified in past earthquakes. Studies had very early on studies and observations linked the performance of these buildings really to their diaphragm and how well their diaphragm performed, responded, and was connected to the exterior walls. There were some who went so far as to make alternative recommendations that focused on that diaphragm deformation and the diaphragm response. So that goes back to at least the 90s and even the 80s, maybe even earlier. There was an incomplete attempt at preparing alternative design provisions as part of the 2000 NEHRP provision cycle, but that never got completed. And then in 2009, I was working on a simplified seismic design project at the time, and I was asked to lead Project Working Group 3, which was going to develop a standalone provisions for these buildings. We thought at the time, what's easier than designing a box building? And so at the time, we thought, well, we could come up with some very different provisions for it. We considered sort of displacement-based design provisions, et cetera. Those seemed promising, but ultimately, the provisions that we were recommending morphed into provisions that could be easily incorporated into the current framework of the NEHRP provisions in ASCE 7. So that led to the FEMA project in which we are recommending back in 2015 that it be incorporated into ASCE 7, into ASCE 7. And since then, that's actually taken place. So the procedure applies, so in terms of its applicability, the procedure applies to one-story buildings with flexible diaphragms and stiff vertical elements. So by flexible diaphragms, we're talking about nailed wood structural panel diaphragms, and they're nailed to either wood framing or more commonly these days are nailers on top of steel bar joists, and then bare steel deck with powder or power actuated fasteners, screws, and with some deck gauge limitations. So you need to meet these special seismic detailing requirements that AISI prepared, or else you have a large penalty. If you don't meet those special seismic detailing requirements, then you have to use a very low R factor to account for that reduced ductility. From stiff vertical elements, what we're referring to are concrete shear walls, mostly concrete tilt-up walls. And in the colder environments, that can be plant cast, precast that's shipped to the site. And then, but also masonry walls. And you can have concentrically braced frames and other systems as well, as long as they're stiff systems. So a summary of the alternative procedure, the status and the advantages of it are as follows. The period is consistent with that of the flexible diaphragm rather than the vertical elements of the seismic force resisting system, which really has nothing to do with how that diaphragm is going to deform and behave. You have increased diaphragm shear strength in the regions around the perimeter of the diaphragm. It's 10% of the span length to each vertical element. And then for the ductile diaphragms, we want the shear demands in the interior regions of the diaphragm to be reduced. So we use a larger R factor for those portions of the diaphragm. The status right now is it's adopted in ASCE 722 as an alternative procedure, so it's not required. Our hope is that there will be some designers that gravitate towards this system. And as we use it more and more, the procedure will become more and more refined and incorporate more buildings into their applicability of the provisions. So the advantage is really improved seismic performance at the same time, at about the same cost or perhaps a reduced cost for many cases. And then especially if you have longer wood diaphragms. And then if you have shorter buildings, shorter building, then the diaphragm capacity is often much greater than you need to begin with. And so that doesn't change all that much. And if you have a non-ductile system, that's where you may have some real changes to the design. The special seismic provisions in AISI, they're primarily in S400, and they likely result in reduced costs in general. And the reduced cost comes from reduced numbers of connectors for the diaphragm. So the first edition was issued in March of 2015. I mentioned that before. And the purpose of that report was to introduce the alternative procedure for rigid wall flexible diaphragm buildings with wood diaphragms. And the intent was that it would better reflect the seismic behavior and result in better performance compared to buildings designed with the traditional procedure. And the target audience was designers of these buildings. That is, to this day, still our goal is to reach the designers of these buildings. The updated report amends the design methodology for consistency with the provisions in ASCE 7. There are a couple key changes that were made when it was introduced to ASCE 7 relative to the original form. There are new numerical studies that address the bare steel deck diaphragms based on new research. And so we now incorporate or allow steel decks in this to use this procedure for the design of steel diaphragms. Bare steel deck diaphragms. We have expanded design examples. Mostly we've added examples that include bare steel deck diaphragms. We did updates to the wood diaphragm numerical studies to reflect a greater range of archetype buildings. Specifically, we were expanding the range of wall weights and wall heights in those studies. And then we had updated discussions of interest to the user, including a series of recommendations for very detailed recommendations for future studies. So the reason why bare steel deck diaphragms were not allowed in 2015 is we had concerns about the ductility of the connectors, and we only had a limited number of tests regarding the connectors. And those tests that we did have showed that there was limited ductility and deformation capacity, raising questions regarding the potential for performance. At the time, we did know that the PAFs and screws would behave better than the welds and button punches, but we really weren't convinced that we knew enough about how they would behave to incorporate it into the document. So what really changed is the additional study by Ben Schaefer and his colleagues. And they included some very good additional connection tests for these steel fasteners that solved some of the issues with original testing. And then they did some detailed three-dimensional nonlinear response history analyses that were very essential for understanding the overall behavior of the steel deck, and to realize, it helped us realize just how different the steel deck behaves compared to the wood deck diaphragm. What are those differences? And I'll talk about those later. And then it led to the ductile detailing provisions in AISI. So the purpose of the report, of this updated report, is to present the alternative seismic procedure as it's incorporated into ASCE 7. The primary audience is still practicing engineers that are designing this type of building. And the intention is to convey design principles to these engineers so that they improve the seismic performance of these buildings compared to how they were designing them using the traditional approach. So at this point, I'd like to do, Kiara is going to do a poll.
Great. So this question is about your relationship with rigid wall flexible diaphragm buildings. So are you a structural designer? Are you an architect? Are you an evaluator of existing buildings? Are you an owner of a rigid wall flexible diaphragm building? Or are you just a big fan that doesn't fit under one of these other options? So it looks like about more than 2/3 of you have already responded. I'll give you a couple more seconds. Hopefully this is an easy one for you. All right, great. So Dominic, can you see the results?
So the results are very good. It looks like I am reaching structural designers with this seminar. Looks like some evaluators of existing buildings. We've talked a little bit about how this procedure might be adapted to existing buildings by doing some renailing, et cetera. Some of the principles you could incorporate it possibly if you do a re-roofing as part of the upgrade. And then a few owners' representatives, that's always good. It's good for them to hear how because they could have a big influence on how these buildings are designed in the future. Okay, thank you very much.
Great, I just closed the poll.
Okay. So what are these buildings? What they are is they're a classic ones like this, probably a distribution center shown on the right. You see a wood panelized roof system on steel bar joists, a wood panel diaphragm. And then you see on the left, those are actually plant cast, precast panels. They look a lot like tilt-up panels here, but in the Northeast where we have cold weather, they tend to be cast in a precast plant and shipped to the site and then erected. So primarily precast concrete, either site cast or plant cast, and then lifted into place. You can have masonry walls and other walls. Cast in place walls are probably very unlikely. And then they will often have brace frames in them. And you combine that with the flexible diaphragm, you get the rigid wall flexible diaphragm building. So how have these buildings performed in the past? So starting really with the Anchorage earthquake, we saw several collapses of this building, and then all of the sort of major earthquakes that followed it, such as the San Fernando earthquake, Morgan Hill earthquake, Whittier Narrows, Loma Prieta, Landers, Big Bear, and Northridge. There were additional failures, and many of those failures, as you see here, have to do with detachment and then partial collapse of the roof structure. So the roof was no longer attached to the wall system, to the walls, that is. And so there's a lot of focus on this poor out-of-plane wall anchorage due to, in part due to cross-grain bending and too low an anchorage design force. And that led to many code changes that made very specific improvements to the design of these structures. This chart, this image figure prepared by John Lawson is very useful for looking at how these design of these connections, the wall anchorage has evolved with time. So if you look at starting with the San Fernando earthquake is when we saw the addition of the design for wall ties, cross ties. Wall ties and cross ties were now required. You no longer could use wood cross-grain bending. And then sub-diaphragms were introduced in the mid-1970s, then Loma Prieta. And also, following that earthquake, the anchorage force was increased. And then after the Loma Prieta earthquake, we had another bump in the wall anchorage force. And then Northridge happened, and we had another bump in the wall anchorage force. And not only that, we introduced requirements for wider wood framing when you had a lot of nails into the boards. And so there's been a lot of improvements. And at this point in time, the thought is with the seismic coefficient being over 1G, we think that essentially elastic behavior is happening at the wall to the diaphragm to wall connections. Okay, so assuming that the wall anchorage issue is solved, really what could happen in future earthquakes that could come into focus? Some of them are P delta instabilities of the walls and columns, given how large some of the diaphragm deflections can be. Effects of building irregularities, such as irregular shapes, non-parallel wall systems. They have these wall bump outs to provide some relief along the exterior view of these buildings. Effects of mezzanines, deformation, compatibility at diaphragm to wall connections needs to be thought of carefully. C-shaped system inadequacies. I'm going to talk a little bit more about these C-shaped systems that appear in low and moderate seismic regions, and joist rollover, which is also used in low and moderate seismic regions to transfer loads from the roof diaphragm to the walls. So just looking at, how does a rigid wall flexible diaphragm response differ from a typical building? So the rigid wall flexible diaphragm building is shown in plan view of the roof on the upper left, and you get a total displacement in the middle of the diaphragm that's a combination of the deflection of the walls and the deflection of the diaphragm. And usually that diaphragm deflection is at least one order of magnitude greater than that of the wall deflection, and sometimes two. So there's a very large difference in the contribution of displacement from the diaphragm versus the walls. And then as that diaphragm moves out like that, it creates leaning columns and leaning walls that the vertical wall system that creates a force that needs to transfer through the diaphragm into the end walls of that building. And if you don't have enough strength or load path to get to those end walls, you risk the chance of a P delta collapse. And so that's how the ultimate concern with how the building strength would be defined. Compared to a typical building, which is multi-stories, you have a roof displacement, which is almost entirely created by the deformations of the braces, such as brace buckling and elongation, and column shortening and lengthening, and that the diaphragm deflection is essentially negligible. And once again, you have to move that roof out or move a story out to long ways in order to create a P delta problem. And then the moment frame is also really just bending of the beams and columns lead to the roof displacement, and the diaphragm displacement's negligible. So the big difference is whereas the rigid wall flexible diaphragm building has very small vertical element displacements, a typical building has the significant movement is in those vertical elements. So looking at a comparison of the traditional design approach versus the alternative procedure, they're both force-based. The magnitude of design forces for the traditional approach are based on the vertical in-plane elements, the properties of those elements, and compared to the alternative procedure, you base the magnitude of those design forces on the diaphragm properties. The period for the traditional approach is based on the vertical elements, whereas for the alternative procedure, it's based on the diaphragm properties. And the response coefficient for the traditional approach is based on the vertical elements, and whereas in the alternative procedure, using an R of diaphragm. And then diaphragm yielding is not addressed in the traditional approach, and it's specifically addressed by strengthening the end regions of the diaphragm which tends to move the yielding to the interior portions of the diaphragm. So there are limitations placed on the use of this alternative procedure in ASCE 7, section 1210.4.1. All portions of the diaphragm must use the rigid wall flexible diaphragm design procedure. Your wood structural panel diaphragms need to be on wood framing or nailers, and you design those in accordance with the NDS special design provisions for wind and seismic. And the bare steel deck diaphragms are you're designing in accordance with AISI documents. And toppings of concrete or other materials are not permitted. So other limitations include horizontal irregularities. The only horizontal irregularity that you're allowed is the reentrant corner, because you can break that diaphragm up into rectangular segments and support it along on each perimeter segment of the diaphragm. What's not allowed at this point in time is non-parallel systems, such as the wall on the right. And if you look down on a bird's eye view of these buildings, you'll see that many of these buildings do have these irregularities. And so it would be very helpful in the future to incorporate these into the design procedure. I had mentioned before that I wanted to talk a little bit about the C-shaped wall systems. They're not allowed using this procedure. Currently, they're not allowed in high seismic zones, but they are used quite a bit in moderate and low seismic zones. And the approach is you do this when you have an expansion joint. Sometimes those expansion joints are designed to transfer shear across them, but usually you have no connection regarding diaphragm chords across those joints. So what you really have is walls on three sides of the diaphragm and then nothing at the joint. And so that's what I'm referring to as C-shaped wall system. So that configuration is not allowed, but it is something that I recommend should be studied in the future because of its prevalence in these low and moderate seismic zones. Vertical elements, this is one change between the 2015 version of the procedure versus ASCE 7, how they adopted it. We used to have an explicit requirement that the stiffness of the vertical elements had to be like 4 times greater than that of the diaphragm. And that was removed and based on more of a deemed to comply type provision. So if your vertical elements happen to be concrete, precast concrete, masonry shear walls, concentrically braced frames, steel, etc., these stiff elements, then they're deemed to comply and that you are stiff enough that you could use this procedure. So you can see that this brace frame system, there are many braces in this, shown in the lower right. That would be something that would be very stiff. When we say concentrically braced frames, we're not talking about tension-only braces or really soft systems. So use judgment in terms of applying it and coming up with your stiffness at these interior vertical elements. So the alternative, so comparison, I'm going to do a comparison of the design steps in the next series of slides with the alternative procedure on the left and the traditional design procedure on the right. Both of them are force-based. The alternative procedure, you can use the optional 2-stage analysis for the walls. For the diaphragm is the first phase, and the second phase is design of the walls. You verify, first of all, for the alternative procedure, you have to verify that you meet the limitations in ASCE 7 that I just described, and you have no verifications required for the traditional method. Then for your period determination for the alternative procedure, it's based basically on the diaphragm length. And so it's for a wood diaphragm, that's 0.002 times the length of the diaphragm. And for a bare steel deck diaphragm, that's 0.001 times the length of the diaphragm. And those are calibrated to the studies that we did, the P-695 studies that we did. And they're not meant to be precise values, but they are pretty good fits. And you notice that it really is the only parameter is the length of the diaphragm. That's because as the diaphragm gets deeper in depth, you add more mass and they tend to offset one another. So the period doesn't vary that much by the width of the building. So the vertical elements for the alternative procedure, you would use TA as you would normally do for the equivalent lateral force procedure in sections 12.8 of ASCE 7 versus the period determination for the traditional approach. You go right to the procedures, the section 12.8. Looking at the equivalent lateral force procedure, first step for the alternative procedure is you have to determine whether, if you're a steel deck, are you going to meet the AISI S400 requirements? And if so, then you can design using an R diaphragm of 4.5 for the steel diaphragms, which is the same as what you would use for a wood panel diaphragm. And for non-ductile steel diaphragms or other diaphragms that don't meet the requirements in AISI, you would use an R diaphragm of 1.5. We are essentially asking that diaphragm to remain elastic in that process. Then you have these series of equations that are very much like the base shear equation, CS times the seismic weight of the building, but in this case, it's C sub S diaphragm. So C sub S is equal to S sub ds divided by R of the diaphragm divided by the importance factor. And if you look at that, that's really that's the peak of the spectrum, but you don't have to exceed the C sub S diaphragm in the second equation, 121016b, for when you're dividing by the period. So if you are off of the plateau, this second equation is going to control. In comparison for the traditional procedure, the TA is almost always less than the transition period. So you're on the peak of the spectrum and you're using an R factor based on the lateral force resisting system. And that's usually an R of 4 for an intermediate precast wall. So determining the diaphragm shears, you create a diaphragm with fastening zones using either the NDS SDP WS or the AISI S400 procedures, and then you amplify the shears in the end regions by 10%. The 10% you amplify by 1.5, the 10% regions at each end, and then of a diaphragm. And then you design your diaphragm chords, and then you do not use the amplified force for your diaphragm chord design, and you design your diaphragm collectors using the omega naught diaphragm factor. Compared to the traditional approach, you're using the diaphragm nail zones, once again, but with an R factor, the force is based on the vertical system. You then design the diaphragm chords much in the same way, but you have a different force level. And then you design the diaphragm collectors and their attachments to vertical elements for forces amplified by omega naught instead of omega naught of the diaphragm. So this is this perimeter zone that I'm talking about. It's 10% of the width and 10% of the length. So that's the zone where you amplify your shears by 1.5. That creates an R factor equivalent of 3. And in the shears in the middle, you're designing for an R factor of about 4.5. And that compares to an intermediate precast system, which is usually 4. So the big difference is, especially for wood diaphragms, you're not generally on the peak of the spectrum for a longer diaphragm. So determining the wall, so in terms of determining the wall shears, if you use the optional 2-stage analysis method, You're going to amplify the forces from the diaphragm by R diaphragm over R times R of the vertical system times rho, but not less than 1. And then you're going to determine your wall shear from the mass tributary to that in-plane wall, not the diaphragm force coming from in, but just the mass of the walls that are acting in plane. You add that load using the base shear coefficient based on R and T sub A. And versus for the traditional system, you would use just R for the building and TA and the diaphragm forces that came into that wall. So in terms of, you then compare how deflections are treated. The deflections are explicitly treated in this alternative procedure. You have to calculate your diaphragm deflections and your vertical element deflections, and then amplify them using C sub D diaphragm, and amplify the vertical elements using C sub D for the vertical element, and check that deflection and drift per section 1212, and check for P delta stability. And for the traditional procedure, I'm not sure that diaphragm deflections are always calculated. I think they're assumed to be okay. Technically, they should be calculated and added to the vertical element deflections. You'd amplify the deflections by C sub D, and you check deflection and drift per section 1212, and check for P delta stability. So and then for the top of wall anchorage, nothing's different about this procedure compared to the traditional procedure. The vertical element designs, using this alternative procedure I've already mentioned, you're allowed to do the two-stage analysis method in 12.2.3.4. It's much like the two-stage analysis procedure for a multi-story building with a flexible upper portion and a stiff lower portion. But in this case, your flexible portion is your diaphragm portion, and the stiff portion are the in-plane walls, the in-plane vertical elements, so the stiff portion. Another poll question, Kiara?
Great. So I just launched it. Which type of diaphragms for rigid wall flexible diaphragm buildings are you more likely to encounter in your work? So you can select between wood diaphragms, bare steel deck, a mix of the two, or another type that's not wood or steel. It looks like already more than half of people have answered. So go ahead and get in your votes in the next couple seconds. Don't worry, your PDH does not depend on your answering of this poll question. All right, Dominic, looks like most people have answered, so I'm going to go ahead and share their results. Can you see them?
So, not surprising, a lot of bare steel deck diaphragms. I think that what we're seeing today is a lot of bare steel. Almost all the steel decks designed east of the Rocky Mountains are steel deck. And then the wood diaphragms are really out west and the southwest and northwest. And then there's a mix. The one thing that has happened during my career is that the number of steel deck diaphragms being constructed out in the west has increased. And that's probably why there's quite a few of you that are mix of both bare steel deck and wood steel deck diaphragms. Okay, thank you. So what I'm moving towards next is the examples. Looking at a traditional design example and the alternative approach examples. I'm looking at the same building many times, with different variations. This is a 400-foot long building, 200 feet deep, and it's a structural panel diaphragm. The roof is 30 feet tall, and the top of wall is 33 feet above the floor slab. And then the roof dead load, 12 pounds per square foot. We have half-inch OSB and wide rib steel deck, type B deck, for the steel deck options. This is the high seismic zone, which is defined as S of DS equal to 1 and S of D1 equal to 0.6, risk category 2, and seismic design category D. We have a redundancy factor of 1, and it's designed as an intermediate precast concrete shear wall, R of 4, omega naught of 2.5, and CD of 4. So for the traditional approach, we're just using those values that I just mentioned. But for the alternative procedure, we're using R diaphragm of 4.5 for the wood structural panels and the bare steel deck diaphragms that meet the special seismic detailing requirements. And then we use 1.5 for the bare steel decks that don't meet those requirements. So those are the welded connectors. And then we have a reduced overstrength factor of 2 relative to that of the intermediate precast shear wall, and R of diaphragm and CD of the diaphragm at 3. So looking at the period, the traditional approach for a 30-foot tall building, you get 0.26 seconds. CS for S of DS of 1, you get in an R of 4, you get 0.25. That controls in both the north-south and in the east-west direction. As compared to the alternative procedure, there's an error in this. No, it's it's the next slide. The diaphragm, we get 0.002 times the length of the diaphragm, so that's 0.8 seconds in the short direction and 0.4 seconds in the long direction. And so using S of DS of 1 and R diaphragm of 4.5, you get 0.22. But because we're not on the period is 0.8 seconds, we actually are controlled by we're not on the peak of the spectrum, so we are controlled by S of D1 over T diaphragm divided by R diaphragm, and that gets you down to 0.167. In the east-west direction, we're capped at the peak of the diaphragm of 0.222. Okay, looking at just as a comparison of the forces. So the forces for the alternative procedure in the short direction are significantly lower than that of the traditional procedure, and yet in the longitudinal direction, they're both very similar, and that's because both periods are on top of the peak of the spectrum. You convert those to shears. The shears are a little bit less in the longitudinal direction, but in the short direction, the shears are much lower. But that's prior to amplifying the shears at the ends. So when you amplify the shears at the end, your shears are both at around 1655, right in that range. So they're essentially equal for the short direction. And so then you go to a nailing zones, you create nailing zones for those different shear values. Both of them, you end up at nailing zone 6, which had a capacity of 1289 pounds per linear foot. For the alternative procedure, we did not use zones 4 and 5 because zones 3 were extended closer to the boundaries. As we'll see in the pictures, the next picture will show that better. So comparing the layout, the nailing pattern for the traditional approach, combining both the requirements for both directions, you can see traditionally we would use many more nailing zones than we would for this alternative procedure. And yet at the very ends, it's the same nailing zone. And what this does is it pushes the yielding away from the wall to diaphragm interface and into that zone 3, whereas in the traditional approach, we didn't see that spread. We didn't see nearly as much spread of the yielding in the nonlinear analyses that we did. Looking at the bare steel deck example, we now have the traditional design is going to be the same. You're at a CS of 0.25 So FPX is 0.25 WPX in both directions. And then for the alternative procedure, we have 0.1 times the diaphragm length for a bare deck diaphragm. This is an error for the second row here. The 0.002 should be 0.001. So we end up with 0.4 seconds and 0.2 seconds. Both of those are on the peak of the spectrum. And so we have an FPX of 0.222 WPX. So this is just a comparison of the forces. They're very similar, just slightly less because it's an R factor of 4 on the left and R factor of 4.5 on the right. And then we have this is prior to amplifying the shears. They're very similar shears, slightly less for the alternative procedure. But then when you add the amplified shears to the end zones, you end up having larger shears in the end zones. So you can see because you're up on the peak of the spectrum, you're less likely to be have a reduction in connectors, though it's really unclear where you'd end up in this case. So just talking a little bit about these decks, these steel decks, they're 36, they cover 36 inches wide. In the West Coast, they primarily use the interlocking side laps. In the eastern U.S. or east of the Rockies, it's almost exclusively nested side lap decks. And so just looking at the pattern, how it works, there's slight differences in the pattern. Interlocking deck, you'll notice values for the same pattern will show up a little bit larger in tables, and that's because you get an extra weld per deck sheet because you're welding on both sides of the interlock. But for a nested deck, you get, for a pattern of 36-7, you get 7 welds because you're welding, the flutes are at 6 inches on center and you're welding each end, and you're sharing, those welds are combined. You're welding through 2 sheets of steel where they overlap, versus the interlocking deck, you have to provide a weld to each side of the interlock. So you're not overlapping the steel. Looking at the zones that are used, the zones right now, the thing to take away are we use zones 22 gauge, 20, and 18 gauge. We use 3 zones. Generally, you use fewer zones for a steel deck, bare steel deck, than you do for wood panel diaphragms. And in general, you try and avoid such large multiple changes in deck size. Maybe 1 change in deck size is normal. For this, we use 3 zones for the traditional design, and we use 4 zones for the alternative procedure. Primarily in this example, we're using this to demonstrate the differences in the design. So the traditional design is up in the upper left. And what you notice is that the zone 1 is extended for the alternative procedure, but we end up with a higher zone at the ends in this procedure. So really you have fewer connectors in the middle of the diaphragm and more connectors on the end of the diaphragm for this case. So now I'm going to talk a little bit about the non-ductile welded diaphragm. These are side laps or top arc seam welds and button punches. These are all 20 gauge deck. And the traditional approach, you end up with a force level of 1653 pounds per foot and 2253. That results in, but in the, with an R, this is with an R of 1.5 for the alternative procedure. You see, instead of values like 1653, you're up at 6,000 pounds per linear foot for this alternative procedure. And the reality is, it just doesn't make sense to do a welded steel deck when you are at this point in time, because the values are so high. And so I think that there will be gradual shift towards using more PAFs and screw fasteners. So looking at a zone layout for welded and button punch, this is just to demonstrate how you would do it. Zone 3, Zone 2, normally in practice, you wouldn't do such a small Zone 2. You just extend Zone 3 if you had to in that case. So let's move to the design of the chord forces. This really doesn't change much. It's just WL squared over 8B. And so using the traditional procedure, you have slightly higher force with an R of 5. You end up with an angle of 5 by 5 by 5/8 compared to the alternative procedure with a wood panel. So this had the much lower forces. That would come out to a 5 by 5 by 3/8. So there's a potential you'd have a smaller chord using this procedure if you're not on the peak of the spectrum. Looking at the shear wall design, the traditional procedure, you end up with about 522 kips. That's the 331 from the diaphragm and 191 from the walls on the ends. In the versus the traditional method, you get 248 from the diaphragm, that's the wood diaphragm, and then 192 from the walls. These are essentially the same number because you're using the same period and the same R factor for the wall design. So what's different is the force that you're transferring from that diaphragm. And this is just looking in the east-west direction. This you're in the peak of the spectrum for both cases, and by the time you amplify the diaphragm force, it comes up to the same as the diaphragm force for the traditional method, and so the wall design is identical for the two procedures. Okay, so moving on to the importance of the deflection estimate. The deflection estimates are very important to allow engineers to know which elements, wall versus the diaphragm, are really contributing the most to the building's response. They're necessary to understand the P delta effects. They're also necessary to know the effects on non-structural elements and to check deformation compatibility. So one of the things that we were concerned with is deformation compatibility. When you're moving the diaphragm so much, you're going to get an angle change between the diaphragm and the wall. And one concern that had been raised is prying on these connections. In some limited studies that have been done so far, what we've actually seen is when you push it one way, you bend the flute of the deck, and you go the other way, you bend the flute of the deck different way. And so you end up actually deforming the deck in a way that reduces the prying forces actually that occur on this deck. So this really just demonstrates the need if you had a very heavy gauge deck, you would be more likely to pop off this connector. But for the lighter gauge decks, you're really more likely to just deform the deck. That's the big takeaway from that. Looking at the diaphragm deflections, this is really important because it gives you a sense just how important the prediction of that diaphragm deflection really is. If you use the three-term equation from the NDS's special design provisions for wind and seismic, you get a flexural term, the three-term equation, you get a flexural bending term of 2.09. This is for that 400-foot-long diaphragm, 200 feet deep. You get a shear deformation due to nail slip equal to 4.37 inches, and a chord slip is 0 because the chords are welded across the joints. And then there's a lot of stiffness from the walls. The walls actually act like chords in a way to stiffen up that term. So if you use that term, you have to then amplify by the CD diaphragm, which is 3 times the 2.09 plus 4.37. and you end up with 19.4 inches. And you think, wow, that's like for a 30-foot tall building, that's like a 5% drift. So it can be a big, big number. But it's important to recognize that the three-term equation is a simplification and overestimates the deflection. If you use the four-term equation, you might reduce that deflection by 30%. And then if you look at the results of the studies that we did, this deflection probably is closer to about 10 inches in the end, for this. So the shear wall, looking at the shear wall deflections in comparison, if you just take a cantilever wall system, include both a flexural component and a shear component, that diaphragm, and assume a solid panel, you're going to move 0.03 inches of elastic deflection. When you combine that, when you multiply by the CD factor of 4, you end up with 0.12 inches. So this is like 1/8 of an inch compared to that 19 inches that we did, or even if it were 10 inches, it's like 2 orders of magnitude different. So big, big difference in the deflections between the diaphragm and the walls. And so even if you have some openings in the walls, et cetera, you're going to have a much lower displacement for the wall system than you will for the diaphragm. That's what you learned from that. When you look at the bare deck diaphragm, you end up seeing somewhat different results. Because they're stiffer, you end up seeing much lower deflection. So in this case, adding up the average shear in each zone and the 4 zones and combining them and using stiffnesses out of the deck manuals or the deck manufacturers' catalogs, you come up with about 0.96 inches of displacement. You multiply that by CD of the diaphragm of 3, you end up with 3 inches, 2.9 inches of displacement. So a big difference. So you have an advantage with the steel deck of having a stiffer system. It may shake non-structural elements harder, but it will move less. And so deformation compatibility with those hung elements may perform better. So just looking at some of the differences and characteristics of the wood diaphragms versus the bare steel deck diaphragms. The wood diaphragms definitely less stiff than the bare steel deck diaphragms. Deformation is primarily from deformation at nails, and wood panels remain essentially elastic. The nail connectors have substantial ductility, and you're really relying on that. And most of the deformation is shear deformation, with flexural deformations is only a smaller portion, smaller component of that deformation. Not insignificant, but smaller. Versus the bare steel deck, definitely stiffer, especially systems that are classified as meeting. You have to classify them as meeting or not meeting the special seismic provisions. And most of the deformation is shear deformation. The warping and in-panel shear of the deck is much more important than it is for the wood panel diaphragms. So the special provisions include not only prescriptive provisions to meet special seismic design detailing. It's really saying use PAFs and screws, but it also provides a method for connections to be qualified through testing and principles of mechanics. And at the time I prepared this presentation, there were no systems that had been qualified in this manner up till now, but I do know that there are deck manufacturers and perhaps connector manufacturers that are working on these proprietary connectors and connectors for the future that they'll be able to get into the system as deemed to comply through this alternative method. Just looking at what I'm talking about in terms of ductility, this is just a connection, a nail connection. You see it's got a strength little over 300 pounds per nail, and a lot of ductility. You can move it, half an inch. Compared to PAF, you can also displace about half an inch. You're tearing at the deck when you do that, but it is quite ductile. Versus the welds, you really can only move a small fraction of an inch before you fail the weld. So the welds tend to be very strong. Here you see a weld with a strength of 4 kips. So the vertical axis on these two are not the same, not one and the same. Very strong, but very non-ductile.
Hey, Dominic, I'm going to interrupt you just to let you know we have about 15 minutes left until we want to go to the Q&A.
Okay, thank you.
Thanks.
So just looking at studies, the studies identified the need for this alternative procedure, and the studies that we used to actually justify the alternative procedure. We evaluated the adequacy of the traditional design, then we evaluated the adequacy of the alternative design, and this evaluation was done in accordance with FEMA P-1026, which included a series of nonlinear analyses. The objective is to have less than 10% probability of collapse in an MCE event. So what we're really doing is, I showed you that diaphragm deflection, building wall plus diaphragm deflection. When that moves, it creates a P delta effect due to the leaning columns and leaning walls. And that can lead to an instability when you move too far. And so when the analysis predicts collapse, that's what we target as the limits of how far you can push the system. So the system, we're using 22 historic ground motions, and we amplify them until we fail the building. We have numerous wood structural panel, diaphragm, and bare steel deck archetypes. We study both high seismicity and moderate seismicity, and we use the connector database that was available at the time in 2015, and then for the update we incorporated the results using additional connector database, the additional connectors database. So the archetypes, we had wood structural panel diaphragms, the bare steel deck diaphragms with PAFs and screwed side laps. We had bare steel deck diaphragms with welded structural fasteners and welded and button punch side laps. We studied diaphragm aspect ratios of 1:1, 2:1, and 1:2. We did large diaphragms that were 400 by 400, 400 by 200, and 200 by 400, and small diaphragms that were 100 by 100 and 200 by 100. This is just an example of the archetype for a traditional approach. We had 6 nailing zones. I discussed other details of this earlier when we went into the design example. So we took the connector database. We used those results in a diaphragm submodel, I'll call it, where we were modeling each connector. And from that, we determined springs. And then we created a simplified building model that consisted of masses in those springs from those subdiaphragm models. And then also we had some masses in springs along the height of the wall as well. And then the stiffness of the end walls and the mass of the end walls. So the evaluation findings were that smaller wood structural panel diaphragm, rigid wall, flexible diaphragm building performance groups failed the procedure. So the smaller wood diaphragm buildings, both the large and small bare deck rigid wall flexible diaphragm buildings failed the procedure. So the traditional procedure didn't work. Some further detailed analyses of using mechanically fastened roof systems show that you do pass the P-695 barely with the traditional approach, but only for the mechanical fastened systems, not for the welded system. So much like the larger wood diaphragm buildings, you can show that they work, but the performance isn't as good as it is for the alternative procedure. An R factor for these non-ductile systems, an R factor resulting in nearly elastic behavior is required. Just going back to this, a reminder from what I showed earlier, the new tests are nice. They have multiple connectors in line. This helps to, a big difference in these tests from previous tests are they've reduced the amount of noise from diaphragm shear deformations and warping. So they were controlling that in this test better. And so you had more of a true vision of what the how the connectors were performing. Then they did this very detailed 3D modeling of it. They took the cyclic connector tests, and much like we did in the original modeling where we came up with new springs, they created new roof submodels that could be input into this 3D model that would be that would account for the characteristics of the diaphragm sheet plus the connectors. So the results are for mechanically fastened roof diaphragms, the ductile connectors resulted in good performance, and that the welded and button punch needed to have essentially an elastic behavior. That I already talked about. This is looking at the alternative rigid wall flexible diaphragm procedure, that we also studied. So I've now moved from the traditional approach to studies on the alternative procedures. So this was the primary, one of the archetypes for wood diaphragm. In this, in the results of these studies, we found that all of the wood performance groups passed quite easily. The bare deck diaphragms, we learned a lot about the bare deck diaphragms from that original analysis, and they also passed with this. What we learned is that we had included too much ductility for the welded connectors originally, and so that they really need to be removed from the test results, the original test results, because they really were not fully represented because they had too much ductility, more ductility than they really have. We had overall diaphragm performance is much affected by the deck profile and the resulting warping and shear deformations. The ductility of the mechanically fastened roof deck system is not as ductile as the connection level testing suggests. So I showed you very good ductility for these mechanically fastened deck system. When you go to the whole system, it doesn't behave quite as well as the individual connectors behave. The detriment in ductility for welded deck systems is not quite as bad as the more recent welding tests suggested. So it's somewhere in between what we had used the first time around and then those that Ben Schaefer's group had used the second time around. The impact of damage to side lap connectors is more favorable to the overall shear deformation response than damage to the structural connectors. So if you have an option of controlling whether the side laps fail or whether the structural fasteners fail, it's better or more favorable to have yielding of the side laps. And then welded steel decks should be removed from I already talked about this last bullet. And so based on this, so I've talked about this, the results just showed justified using an R of 4.5 and the alternative procedure for the mechanically fastened steel decks. Looking at recommendations for future studies, these are the priorities. We have many more than just these 5, but I'm just going to talk about these because we identified these as the most important. The applicability to buildings with lightweight enclosures, such as steel bracing systems and other steel bracing systems and other special seismic force resisting systems. So what we want to know is, could you use this system with a lightweight wall system? So it would be, and with a vertical element that's maybe not so rigid in the end. Is there a way to modify the procedure for that case? Irregular plan shapes is very important. Abrupt changes along exterior walls and non-parallel wall systems. We think that this study is very important because there's so many buildings like that out there, and will be built in the future. We also looked at some of the applicability of this building type to buildings with mezzanines and multi-story buildings. I know that I worked on a fabrication building once that had steel deck diaphragms spanning nearly 500 feet, and it was a 2-story building. So could you modify these procedures for that design of that top story of a multi-story building? And then C-shaped lateral system configurations. I think that there's a possibility that this approach could be adjusted for such a system.